Hello everyone, welcome to my talk on scalable language-agnostic taint tracking using explicit data dependencies. This work was part of some of my PhD contributions to an open source project called Joern, and I'm presenting this on behalf of the contributors and Fabian, who is the prime owner and maintainer of the Joern project. So what is the motivation for having this kind of data flow analysis in the project? And well, the motivations are that whole program analysis is expensive and difficult to scale, and if we want to try to ignore the external libraries and reduce the problem size, we have additional challenges, such as how do we model and define the behavior at call sites that have unresolvable callees, and if we do summarize this in some way, how precise should these summaries be, and can we achieve quick feedback without sacrificing recall with all the way to solve those additional challenges. This is a motivating example we use in the paper, and just to explain it briefly, we have object U defined by a static external call get value. Then we have a object V defined by a simple constructor. We then have an external config call that defines some control flow, and we have another definition of result, which is the return value of a dynamic dispatched call, u.transform v, and then we have the result of this and v as parameters to an internal static call bar, which then passes the parameters to sync.addValue. So this perspective of arguments to calls and operations being defined, used, or both within a method can be represented by a data dependence graph, which is the stable representation that we use. And the edges on this graph go from where variables are defined to nodes that use it without a prior redefinition. And if we add control dependence, we can get the program's dependence graph, which is what we'll use to visualize this code later. But the big question now is, how do we handle callees that we cannot see? So these external libraries that we are ignoring. Well, so we have in the blue rectangles, the declarations, and we can see at the top that U and V go to our u.transform V result, and then we have that result goes to the internal call bar result V. But how do we encode the possible data flow side effects that happens in u.transform V, as these objects could have sort of the data flow from V could affect the receiver U in some kind of way. There could be side effects that set fields or load fields from receiver to the result of the call, etc. So that's really the big question. How is this going to be encoded? And well, we choose to use the system dependence graph representation, which has separate nodes for the in arguments and the out arguments. As an example here, we show that the transitive dependency, which is essentially a dependency between two nodes that undergo a number of steps in between by a single edge. So by the presence of an edge between input argument U and output argument U means that data flow is retained, but data flow from U could flow to V, and perhaps V is the only argument that defines the data flow in the return value. So this presents a call site local transitive dependence representation. So extending this by over-approximating our data dependence graph, we can then encode via the output arguments that U and V might actually have some kind of implicit flow to the call of bar that is first dependent on this transform call. So the proposed solution is a whole program dependence representation that can be updated when the behavior of calls to external libraries becomes known. So these transitive dependencies between the input and arguments at the call sites are encoded with the system dependence graph approach, and we allow users to annotate what actually happens at these call sites without recomputing the whole graph representation. So this is also important to support partial program analysis to keep the problem small, but remain sound by default when we encounter unresolvable callees. And sound means that we assume that all input arguments use and define all output arguments and the return value, and we remain intra-procedural until query time, so that we're isolated from the call graph analysis, which could be changed at some point. The approach is built on the code property graphs generated by Joern, which I briefly mentioned is the open source project this is contributed towards. So first we add a stable data dependence representation on top of the CPG. And the way we do this, so that we don't have to recompute the graph every time that we maybe redefine the behavior of a callee, is over-approximating all the call sites as if they are unresolvable callees. Of course, this will introduce many invalid parts, but these will be discarded at query time. And this is either done by analyzing the data dependence. If the callee is resolvable, we can then actually perform a data flow analysis on that procedure, or refer to a user-defined semantic annotation if one is supplied, which I'll go into detail later. So obviously, because it's over-approximated, discovering additional flows requires no effort. That is the default. And annotations only are required if we encounter false positives that we would like to eliminate. So annotation language is very simple. It mirrors this input-output pair logic. It consists of the procedure's full name and the input-output pairs, which define the edges between an input argument and an output argument. And if no edge is present when a summary is present, then it is assumed the flow is killed or sanitized. The parameters are either by index or name, as some languages use named arguments, and special indexes are used for the return value, so -1, and the receiver 0. Such an example looks as follows. So if we want to describe that Euler transform V sanitizes argument 1, and the receiver propagates flow to the return value, receiver is 0. Since receiver is not sanitized, we must have the sort of default edge, so 0 to 0, and that 0 goes to -1, the return, to describe the data flow between the receiver and -1. No pair is present for the first argument, thus it's assumed to be sanitized. For example 2, let's assume that the receiver taints argument 1, and neither argument defines the return value. Then we can have our 0 to 0 and 1 to 1 to say that neither argument is sanitized, but that the argument the pair from 0 to 1 describes that the receiver taints argument 1 in the output. So a very simple annotation syntax that is quite easy to write, but again, the limitations we'll just go into a bit later. So how does this work when we actually encounter internal procedures? And this is where I describe on a high level the algorithm of the paper. So the query, this is sort of now the on-the-fly query data flow analysis, consists of a set of sources, a set of sinks, and the user-defined or generated semantic annotations. As the semantic annotations is also attached to a programmatic API that one can generate from the CPG itself. And the goal is to determine all source sink pairs for which there is some kind of transitive dependency. And how is this practically done? Well, we break the query up into tasks, and the results from each tasks could either be standalone or generate new tasks to be solved at method boundaries. So such an example could look like the following. So we have our semantics. This is Scala code, by the way. Joern has a default semantics object that describes basic operators. And then we have our engine context, which is a simple configuration object. And then we define our source query, which has the cpg.call step describing the call, or the return value thereof, the sink, which will describe the argument 1 of add value, and then we call our reachable by query. So we begin by just creating initial tasks. Initial tasks will be based on the sink as we do backward analysis in this example, and this will be the 3-tuple of a node, initial empty path, and the call depth. Now, before solving any task, let's consider what a result look like, as these results will create new tasks. So we have 2 main parameters, which is the path and the call depth of a result, and the path is consisting of a list of tuples, where n is the path length, v is the node, and a boolean indicates some sort of completeness. And what this completeness is a boolean indicating whether the associated method of this node has been resolved in the process of generating this task, or resolving it has been deferred to a future task, which means that we'll essentially be creating new tasks from this node. So how are new tasks created from incoming results? Well, this is a k-limited analysis to ensure termination. So we first ask, is k larger than our maximum depth? If yes, do not generate new tasks. What this results in is an incomplete tasks with no dependent task, and this will ensure widening and termination. First is v1 a parameter, so we start at, since we're going backwards, we're sort of looking at the head of the path. So if yes, look up the corresponding argument against the call graph. So whichever call graph is in place, if none, then this will approximate. And then generate the task as follows. So we have our 3-tuple of the argument, the path, and k plus 1. Is v1 an argument to a call without an associated semantic? Then, and r1 is false, so it's a incomplete item. Then if yes, the corresponding output argument will be the node of the task. And just to note that operators are also modeled as calls, so this includes your assignments, generic binary operators, etc. And how do we solve these? So a task, again, is this 3-tuple, and assume we have a global result cache to memwise incoming results. So for each outgoing DDD edge, we have SO, which is the parent of V. Is there an edge between SO and V that is valid? So recall that every DDD edge is over-approximated, so it's not necessarily valid by default. The validity depends on if there's a semantic definition that says this is valid. If it is, then we have a result of S0, and then the second part of the tuple is if it's an argument, an output argument, which will determine if a result is going to, the result is going to be a new task. And otherwise, is there a cached previous task result, in which case the prepending path would be a little bit longer, and we save a bit of computation. To not have incorrect cache results, we have the following cache key, which is the node, the call stack, and the call stack up until that point, and the k depth. Then we, at the bottom, if the result above contains a source node, ensure that one of the result entries starts at the source node. We then deduplicate and return the results of V, and the final result of the query are all the entries in our result cache that begin with something in the source set, and then there's a final deduplication so that we don't return subflows within larger flows. An example of that from Joern is on the table on the right. This is without defining any semantics or imports. The graph on the left I won't explain too much in detail, but as you can see, all those edges are these sort of over-approximated input-output relations that where Joern will assume there is some kind of dependence. And this is one of the flows that's returned to the sink. So for the evaluation, we use taint analysis. So again, we ask, does a source define data at a sink? And what is our indicator of success? Essentially, we use F1 score, which is a little bit more about how many true positives do we get, more biased towards recall. And since that is perhaps too biased to include for something that over-approximates, we also include J-index, which is a bit more balanced for false signal. So we use 3 programming languages to evaluate against, so Java, Python, and JavaScript. And related work that we evaluate is semgrep as the fast, cheap option, and CodeQL as a bit more of the detailed, expensive option. In the data sets, we use Security Bench Micro, Security Bench Micro JS, which is a contribution of this paper, which is a transpiled version of the Java equivalent, and Florat, which is an extension of an existing benchmark that we complete. Just to briefly explain this table, we have Joern with and without semantics. With semantics is the sem entry. So for the Java equivalent, we have better recall and precision than the rest, and faster runtime. But yeah, semgrep has much faster memory, or better memory rather. Then we have CodeQL as the next best in terms of precision, and then lastly, semgrep. The runtime of CodeQL is quite high. And by the way, this is partial program analysis, so the libraries are excluded. Next, for Python, on the second row, we have larger recall, but far less precision. The precision you can refer to the J-index, as we have much more false signal. But again, CodeQL is a bit more precise here, and Joern is the fastest, and semgrep is the least precise, uses less memory. Then with JavaScript, we see that, again, CodeQL has equivalent recall and better precision, but we're still faster and use more memory. But now let's ask about the whole program analysis. So we include libraries. Because Java uses bytecode and semgrep doesn't support that, that's excluded here. The runtime looks a lot worse in terms of the Java example. We're a bit more equivalent to CodeQL. I know CodeQL sort of packs the runtime with it, so perhaps it is doing much more of a whole program analysis than we maybe intend in the evaluation. But we still have a higher recall. In case of Java, better precision. But one thing that's very interesting, besides the high recall, low precision CodeQL trend, is that for JavaScript, we somehow have more precision. So I guess that suggests that having access to the callees actually improves upon whatever is happening in CodeQL. Cool, so let's get to the limitations. Obviously, defining data flow from input to output parameters is very simple. While it is an intentional design decision that makes improves the speed of analysis, it doesn't model field loading and setting in general, object memory and heap, or side effects on modifying global state. The task solving does not account for dynamic object shape properties, so defining properties on the fly. That's something you can do in a lot of dynamic languages. Object aliasing, we do weak updates, and variables captured by closures is not fully baked. The speed and memory part of the evaluation does not isolate the benefits of the underlying database. CodeQL, for example, uses SQLite. Joern uses a columnar graph database. And the precision of the data flow analysis, of course, is tied to the call graph. Whether we can resolve a callee or not depends on when something will be over-approximated. And so to conclude, we present a data flow analysis system in Joern that is capable of language-agnostic analysis, is robust to missing dependencies, allows for annotating semantic behavior of callees in order to reduce false positives, and compared to the evaluated related work, has better runtime performance compared to CodeQL, but is not as precise for dynamic languages, has higher precision than semgrep, but not as performant, but overall has much higher recall than both due to this over-approximation first strategy. Great. Any questions?
Are there questions? So given we have only 1 minute, maybe I would like to ask a question. So in your design, you first decided to over-approximate all of the flows, right?
Yes.
And then later on, you decided to somehow limit this call depth to, I think, 5 or some value
yes,
k.
Yes.
Could you comment on how these two decisions go together?
So I have some extra slides here. Yes. So with the value of k, the higher value is more precise, and also using k-limiting just allows for a much simpler design. And obviously, a high value of k will then become very expensive. The lower value would mean more widening happens, and we have faster termination. But to decide this value, essentially, we took really big benchmarks from various papers. So defects4j is one that's popular, bugs in pi is another. And for varying values of k, we ran a bunch of data flow analysis, looked at a bunch of sources and sinks that are present in each library, and just ran that. And we found that k was a good point before we start to see this massive, sort of almost exponential growth. So that is sort of how we optimized and chose that value. As per CodeQL and semgrep, that equivalent is not extremely configurable from what I had a look.
Awesome, thank you. So then let's thank Sedick again.